To ensure circuit conductivity of the conduit path, the braided cable cover should be clamped around the conduit using a ground clamp and secured with an appropriate electrical fitting. This will create a secure connection between the braid and the conduit, ensuring proper grounding. Grounding the green bond wire at the heater location within the high voltage cubicle is not necessary. The green bond wire is connected to the power panel source, which is already grounded. By connecting the green bond wire within the high voltage cubicle, you could create a potential current path if a high voltage short occurs. It is crucial to maintain electrical isolation between the high voltage and low voltage sections. Grounding the green bond wire within the high voltage cubicle should be avoided. Grounding the high voltage section should be done through the dedicated ground bus with a minimum impedance of 5 ohms. In the event of a high voltage short, the current should be contained within the high voltage panel due to the high ground impedance. Electrical grounding and bonding are critical for safety and proper equipment operation. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices to operate and clear the fault. Bonding connects non-current carrying metal parts to create an electrically conductive path, minimizing voltage differences and reducing the risk of electric shock. The National Electrical Code (NEC) provides comprehensive requirements for grounding and bonding systems. These requirements are designed to ensure that electrical systems are installed and maintained in a safe and reliable manner. In high voltage systems, proper grounding is especially important due to the increased risk of electrical hazards. High voltage equipment and circuits must be grounded in accordance with the NEC to protect personnel and equipment from fault currents and voltage surges. Grounding electrodes, such as ground rods or ground plates, are used to establish a connection to the earth. The grounding electrode system must have a sufficiently low impedance to effectively dissipate fault current. The NEC specifies the minimum size and type of grounding electrodes, as well as the requirements for their installation. Grounding conductors, also known as equipment grounding conductors, are used to connect non-current carrying metal parts to the grounding electrode system. These conductors provide a path for fault current to return to the source. The NEC specifies the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device. Bonding jumpers are used to connect different metal parts together to create a continuous electrical path. Bonding jumpers are typically used to bond metal conduits, enclosures, and other equipment. The NEC specifies the requirements for bonding jumpers, including their size and installation. In high voltage cubicles, it is important to maintain a clear separation between high voltage and low voltage circuits. This separation helps to prevent the risk of electrical hazards and ensures the proper operation of equipment. When installing low voltage circuits within a high voltage cubicle, it is important to follow all applicable NEC requirements. This includes properly grounding and bonding the low voltage circuits. The use of a braided cable cover over low voltage wires in a high voltage section can provide additional protection. However, it is important to ensure that the braided cable cover is properly grounded to the conduit. A ground clamp and an appropriate electrical fitting should be used to create a secure connection between the braid and the conduit. The green bond wire, also known as the equipment grounding conductor, is used to connect the non-current carrying metal parts of equipment to the grounding electrode system. The green bond wire provides a path for fault current to return to the source. In general, the green bond wire should be connected to the equipment and to the grounding electrode system. However, in some cases it may not be necessary to ground the green bond wire at the equipment location. For example, if the green bond wire is connected to the power panel source, which is already grounded, it may not be necessary to ground the green bond wire at the equipment location. Grounding the green bond wire within the high voltage cubicle could create a potential current path if a high voltage short occurs. Therefore, it is generally recommended to avoid grounding the green bond wire within the high voltage cubicle. The high voltage section should be grounded through the dedicated ground bus with a minimum impedance of 5 ohms. This high ground impedance helps to contain the fault current within the high voltage panel in the event of a high voltage short. It is important to regularly inspect and test grounding and bonding systems to ensure that they are functioning properly. This includes checking the condition of grounding electrodes, grounding conductors, and bonding jumpers. It also includes testing the impedance of the grounding system. If any problems are found, they should be corrected immediately. Proper grounding and bonding are essential for electrical safety. By following the NEC requirements and best practices, you can help to ensure that electrical systems are installed and maintained in a safe and reliable manner. Additionally, consider these points. Firstly, understand the purpose of grounding and bonding, which is to provide a low impedance path for fault current, minimizing voltage potential and ensuring operation of overcurrent devices. Secondly, ensure compliance with NEC. The NEC outlines specific requirements for grounding and bonding based on voltage levels and system configurations. Thirdly, when connecting the braid to the conduit, utilize a listed grounding clamp suitable for the size of the conduit and braid. Ensure the clamp makes direct contact with the braid and is securely fastened to the conduit, removing any paint or corrosion at the contact point for optimal conductivity. Fourthly, avoid creating ground loops. Grounding the green bond wire at multiple points can create ground loops, which can carry circulating currents and introduce noise into the system. The green bond wire should be connected to the low voltage panel's grounding system and run continuously to the equipment within the high voltage cubicle. Fifthly, consider the impedance of the grounding system. The impedance of the grounding system should be low enough to allow sufficient fault current to flow, enabling overcurrent devices to operate quickly and clear the fault. Sixthly, regularly inspect the grounding and bonding connections to ensure they are tight and free from corrosion. Use appropriate anti-corrosion compounds on connections in harsh environments. Seventhly, perform ground impedance testing to verify the effectiveness of the grounding system. This test measures the resistance of the path to ground and ensures it meets the required standards. Eighthly, maintain documentation of the grounding and bonding system, including diagrams, test results, and inspection records. Ninthly, ensure that all personnel working on electrical systems are properly trained in grounding and bonding practices. Tenthly, if there is an existing grounding bus within the high voltage cubicle, it's typically designed for high voltage faults. Connecting the low voltage grounding conductor to this bus may not provide the intended protection for low voltage faults and could introduce unintended consequences during high voltage events. And 11thly, the 5 ohms impedance in the high voltage ground bus is intended to limit ground fault current to a level that will not damage equipment while still allowing protective devices to operate. Adding a low voltage ground could bypass this impedance, potentially leading to higher fault currents than the high voltage system is designed to handle. Proper grounding ensures safety and prevents damage to equipment.